Good morning, guys. Today is 2021st. This is Xah Talk Show, and you are welcome to it. And we are going to do Wolfram language Mathematica coding today. And just that topic. I think, post your comments and questions. I think I'm just going to focus on that topic because it's better to focus on one topic. And then next video we're going to do Emacs list coding or keywords. It's better that way. It's better that way because long-term wise, people can who watch my videos offline can focus on that. So today's 2021, August 1st. Wow, today's August. Now August 1st. So today's talk show. Okay, so I'm going to let me tell you what are we going to code today. Welcome, Bart. Good morning, Bart. And we are going to do 3 fantastic subjects in geometry, and we are going to code it with Wolfram language, okay? Wolfram language. So we are going to code fantastic Wolfram language with it. And I'm going to show what to do. So greetings, Code Bamboo. So we are going to, so this is, the topic is geometric inversion. Now that's a process in mathematics. Okay, let me tell you what that is first of all. So here you can see first of all, you see some pretty pictures. Now this is circle inversion, geometric inversion of many circles in recursively nested geometric inversions of circles. So basically you begin with this image on the left, you see 7 circles. Then you invert each circle with respect to each other circle, and you do that about 3 or 4 times, then you got this picture. Isn't that beautiful? Fantastic. Now here's another inversion. So you begin with these 6 circles arranged like that, then you got that. So, and similarly you start with this image, 5 circles, then you invert each and every one with respect to every other one 4 times or so, you got this picture, and similarly and so on. And then in this picture you invert a bunch of lines with respect to a circle in the middle, okay, a grid. And in this picture you invert a bunch of lines arranged in a kind of pentagonal way, and you invert all these lines with respect to a circle in the middle, and you got this picture. Now this photo and this one is an inversion of a grid, rectangular grid, with respect to a circle in the middle. Then you get this image on the right. So this is called geometric inversion, okay? Alternatively, if you know mathematics, alternatively it is the image of the complex function 1 over z. 1 over z. Or is it conjugate 1 over conjugate z? Anyway, it's the same, except it's flipped, it's mirror flipped. Okay, but anyway, if you know what I'm talking about, you know that already. Okay, but if you don't know what I'm talking about, let me explain. Okay, so this is geometric inversion. So geometric inversion is a process in math. Okay, so let me show you. Let me tell you what that is. What is this process? Okay, so here is a picture. Actually, there's a live version. Let me show you. Okay, this live version. So we need to turn on JavaScript, turn it on, and refresh. And let's stop this video here. And good morning, Andy Lee. Those are pretty pattern pictures. So how did you come across this topic of geometric inversion? Well, if you are obsessive about mathematics, which I was in when I was around my 20s, in the 1990s, I was obsessive. I want to become the greatest mathematician. So you read a lot, then you know a lot of topics. Just like programming, you get into all sort of topics. So you can just search for geometric inversion. There's a Wikipedia article. Of course, I did this in the night. You see all these pictures? I did them in 1990s, mostly 1996 to 1999. Okay, all these pictures. So you can see they are not anti-aliased. You know, by today's standards, it's kind of lousy. And today, in fact, you should have dynamic. You know, you should move your mouse and drag the circle around and see them change dynamically. With JavaScript, which I'm getting old, I wanted to do that like 5 years ago. I still haven't done so. But anyway, today we are going to use Mathematica to code this. So all these are done in Wolfram language back in 1990s, 1997, 1998. And today, you know, you go to, okay, so let's go to Wikipedia. But mostly, I'm just going to show you how do you code these, okay? So the inversive geometry, okay? It's kind of called inversive geometry, but I'm not sure that's a good term. So they explain, here is a Wikipedia, they explain the process, how you do it. I'm going to explain, okay? And this is also a fantastic idea, okay? By the way, actually, I might be able, you know, I might show you how to code this. So given a hyperboloid we talked about a few days ago, this shape, if you invert it with respect to a sphere in 3 dimensions, you know, then you get this surface called cycloid. Very fascinating. Okay, so geometric inversion is it's kind of a general concept. You know, if you study math, especially if you are a geometer, it's one of the things you must know. But let me also mention, this is not in the standard curriculum. Let's say you studied calculus for 2 years, one ABC, you know, all the calculus for 2 years in high school or in college. But you may not know this concept because, I mean, if you have a math degree, you know, bachelor's degree. Let me close the door. You still may not know this concept because that's another topic. Because math, just like, you know, math is big, okay? So, but this is but if you have a math degree, you may not still know this concept. You probably will, but maybe not much. However, if you are a good mathematician, then you know this concept for sure, okay? Geometric inversion, especially for geometers. Now, let me explain what it is, okay? So so let's begin with this. So geometric inversion is a process, okay? It's like a function, okay? A function where the parameters, so first of all, let me explain it geometrically. So it requires a circle, okay? So it's a function, first of all. Forget about requiring a circle. So it's a function in the plane. Let's say the 2-dimensional case in the plane. So given any point, you apply the geometric inversion, you get another point somewhere else, okay? So first of all, understand it. It's a function. It's a mapping from a plane to a plane. Okay. So if I have a point P, where does it map to? Let me explain. Okay. So in a Cartesian coordinate, so this is a circle of radius 1 at the origin. So given any point on the plane, you draw a line from the origin to the point, then you actually I explained here, but let me think if I can remember it without, you know, you can actually read it. Equals to r squared. Yeah, okay, I got it. So this circle has a radius of 1, okay? So what is, given a point P, what's the output? What's the point Q? So the point Q is, so basically the distance from origin to P times the distance from O to Q equals to 1, or r squared, whatever is the radius. The radius here is r. So you can see from the picture, if Q is far away, the new point is inside the circle. If Q is close to the circle, the new point is close to the circumference. If the P is inside, then the result point is outside the circle. So that's a geometric inversion. So this concept, so you can see why it's called inversion. So basically, every point outside the circle becomes inside the circle. Every point inside the circle goes outside the circle. Any point on the circle doesn't change, remains the same. Okay, so it kind of swaps the plane inside out. So in another sense, this is kind of mirror. So every point outside the circle got mirrored inside the circle. You will see that in a moment. Okay, so this is called inversion, and it's of course, like I said before, it's related to the inversion, like 1 over x, especially in the complex plane. It's like, so you can also see that from the definition. Okay, so let me go back here. So if you read this page, just search for geometric inversion, XahTV, you'll find, step-by-step explanation what it is, okay? So now, geometric inversion is a function on the plane. Let's limit to the plane case, but it also works in 3-dimensional Euclidean space, or 4-dimensional or higher dimensional Euclidean space, okay? But let's just talk about the plane case. So first of all, it's a function, okay? It's a function that maps any point on the plane to another point. So once you got that idea, you can see what happens if you draw any shape, like a circle or whatever shape on the plane, and you try to invert it. What is the result? Okay, so there's some theories. Any line inverts to a circle, and any circle inverts to a line by itself. Okay, so in other words, if you have a circle, and you invert every point on the circle, what is the result? Usually it's another circle, okay, smaller or bigger. If the circle is outside that center circle, then it becomes a smaller circle inside the circle. So anyway, basically the theory is that circle and lines inverts to themselves. Circle becomes circle, lines becomes circle, circle become circle or lines, okay? So so here are the four different cases, limiting cases. So you can see, so here is a animation. You can see here is an animation. You can see now this yellow open image in a new tab, okay? There's a yellow circle on the origin. That is an inversion circle. You cannot see. The dotted circle are the circle you want to invert. Then the other red one is the result. Okay, so that's kind of the animation. So oops. Close the browser by mistake. Okay, reopen last page. Go back. Okay, cannot go back. The university geometry. So let's go back to. So it relates, the geometric inversion relates to inversion or inverse multiplication, or especially in the complex plane, complex numbers. Okay, so let me start to code Wolfram language. Okay, that's an explanation about this page, about what inversion is. So if you begin with a bunch of grid lines like that, you invert them. Here is a result. Okay, so all these lines become circles. This is kind of very interesting because it swaps the plane like inside out. So outside comes to inside, inside comes out around the circle. So this is what happens. So you might wonder, why is there a hole in the middle? Because you see, we begin with this grid. If all these lines extend to infinity, then there will be no hole. You are seeing the hole because this kind of a club-shaped hole is actually the boundary of the square. You see, but if your square, if your grid is infinite in size, there will be no holes. It forms a hole because things outside comes inside, so that's why you see that. So it's fascinating. And then there's many, for example, this linkage we talked about, highly important in robotics today and in the past. So this linkage is based on the idea of geometric inversion. Basically, so it converts rectilinear motion to a circular motion. Okay, so how do you do that? Let's see. How do you okay, so you can see the red line is a rotational motion, and the blue line is a linear motion. So if you are doing mechanics, robotics, you need some kind of this conversion, linear motion to rotational motion. Now, how do I show this as a good example? Yeah, okay, so this is, anyway, this linkage is called Poisselier linkage. You can see it on Wikipedia, by the way. Okay, so enough talking. Okay, so let's code Wolfram language. How do you actually create this image? Let me show you. Okay, so let's start coding Wolfram language. So first of all, what is the thing we want to code? Any questions? I'm getting into math, starting with algebra and trigonometry. That's great. So we want to start to code. Okay, let's see what I want to code. So I want to code this one. Okay, so yeah, so let's start to write code. So how do you let me think. Okay, square. Okay, first of all, let me see if there's a square function in Wolfram language. Magnify. So square. Okay, so this is not okay, so that's not what we want. First of all, we want a graphics primitive. So we want some function to represent a square. Okay, so let's say polygon. Let's go to talk show. Let's go to today's talk show. Let's start some Wolfram language, and let's start to code some polygon. Okay, polygon, and the polygon. So 4 points. Okay, so this is a plane, 0, 1, 0, 1. Start with 0, 0, 0, 0 to 0, 1 to 1, 1 to 0. Yeah, so okay. 0, 0 to 1, 0, 1, 1 to 0, 1, then back to 0, 0. Okay. So that's our polygon. Okay. So, and let's graphics 3D. Okay, okay, that shows a square. Now let's say axis true. Okay, there's no there's no axis. Oh yeah, so I played, this is wrong. Yeah, so now axis. Okay, so now you can see that the axis we have a square of of a side length 1. Okay, but let's see cube. Cube represents a rectangular cube centered at origin and unit length. Okay, cube is 3D. I want a 2D square. It doesn't seem there is a square function. Let's do this. Okay. Anyway, so let's say polygon. Yeah, what are we doing? So we wanted to generate this. So the idea is that begin with one square, then you create lots of unit squares forming a grid. Then you apply the inversion to them all. Okay, so let me just code it quickly. So first of all, table, okay? Table x, y, x from 1 to -5 to 5, y from -5 to 5. So we got a matrix, okay, a bunch of coordinate values. Then let's name this grid points, okay, grid points, bunch of values. Then we want to map this. Let's do a 3D case, okay? Let's do a 3D case. Cube. Let's see, cube represent a cube with edge length. Cube centered at that. Rotated by an angle with respect. Okay, cube represent a cube centered at. Okay, let's try the 3D case. Let me just code it. So if we do 3D case, let's see. Then z 0, 5 to 5, okay, x, y, z. So now we have a three-dimensional matrix. Now actually table, okay, so cut it. So we want a cube with these points and length 1, okay. So we got a bunch of cubes. Now graphics 3D, okay, grid points, okay, show it. Okay, so we got a bunch of cubes. You know, I'm trying to do a three-dimensional case here instead of, you know, I can do two, but you know, this, the way I code it just happens that perhaps let's try the 3D case first. Okay, so so we got a bunch of cubes. Now we want to shrink each one a little bit. So we don't want wait. Oh yeah, so wait. Okay, so we got a bunch of points. Let's see. Let's say smaller. Let's say 6. Okay, so we got lots of grids. Now let's define an inversion. Okay, so inversion with respect to let's define a inversion function. Okay. Now, is there a there's no, I don't think there's a built-in inversion, but it's so trivial, that is why they don't have a built-in. So let me just define it myself, okay? X, Y, Z, those are the input, and the output is going to be, okay, what is the formula for geometric inversion? Okay, here. So you can see here is the formula, kind of paste it. Let's prettify, okay? So R is, let's say R, okay? R is the radius. Now, so this is a 2D case. Now we want a 3D case, AB. So what is the A and B? So inversion of XY is centered at AB, okay? So yeah, okay, so let's do circle A, B. So A and B is the center of the circle. This is a 2D case, okay? A and B is the center of the circle. R is the radius. Now, normally, in the normal case, we assume A and B is 0, 0, okay? So, and R is 1. And XY is the input. So this will return, this thing will return the, the new point of the geometric inversion, 2D. Let's say 2D. Okay, so yeah, so that is the case. Okay, so let's try. Let's try 1 and 1. Okay, so what happens to the point 1 and 1 if we invert it with respect to a circle at origin and radius 1? Okay, now what if we give it a symbolic result? So here is a symbolic result, very simple. So that's a 2D case. Let's write a 3D case, okay? Let's write a 3D case. Now the 3D case is Z 3D, so A and B and C. So this is a circle. Now in 3D you have one more coordinate. C, and so here will be Z minus B, ABC, R, right? Plus I think that's it. Can we do that? Yeah, so this is the 3D case. Now let's double check? Okay, let's double check. Let's double check. Okay, so let's XYZ, ABC is the center of the circle, R is the radius, so XYZ is the input point, so X minus A, Y minus B, Z minus C, okay, then times R squared divided by that. plus ABC. Okay, I think that's right. So now let's call it. Okay, let's just copy that. Copy, paste. So in general, what happens if you invert it, okay, to a circle? Yeah, 3D, 3. Okay, so here is what happens in general. Okay. Okay, so fine. So let's try to invert this cube. Okay, so let's we have a bunch of cubes. So cubes, now we have a bunch of cubes. We want to apply this to the bunch of cubes. What is the bunch of cubes? Let's see. I want to see what is the I want to see what is the what is the structure. Okay, so let's see. So cubes, so anything cubes, apply inversion. Okay, got it. So that I'm trying to see the structure of this cubes expression. So now I know the structure, I can do transformation on it. So cubes, so any cube cube has a radius. Okay, so radius will become geometric inversion 3D, apply the point of the cube and apply this. Okay, copy it. Let's just copy it, and here is just P. Okay, so this is what we want. Yep. You see, we have applied the geometric inversion 3D to the center of cubes. So this is a result. So we can actually show the result. Let's hope it works. Shit. Cubes. Oh, okay. So wait, what? What is the error? Cube is not a graphics 3D primitive. Why is it not? I thought it is. Cube is not a graphics 3D primitive or directive. It is. What are you talking about? You see, cube can be used in graphics 3D. Let's try again. Okay, so let's close that. Don't save. Okay, what's going on? Oh, we forgot the XYZ. Did we forgot the... Oh, we forgot the Z. Yeah, so you see the Z is not evaluated to a number. So why is the z not evaluated to a number? So cube geometric inversion p. So let's try that again. Oh yeah, so so we need to evaluate this, do it, okay, then show it. Okay, now we got the actual cubes. Now we do this infinity. Okay, forget it. You know, you got infinity when a cube is centered on 0, 0. You know, you cannot. You see, you cannot invert when a point is at the same as the inversion circle. Okay, so anyway, anyway it should work. Okay, so let's show the previous. This better show, my friends. Okay. Oh, okay, so I know what's going on. So we got this. Okay, one more thing to do. Let's see. Oh yeah, so so we got one more thing to do. So we got this error because we need to discretize the cubes, essentially. So that's right. Okay. Okay. So we got a cube geometric inversion. We need to apply the inversion to the we need to apply the geometric inversion to the coordinates of the cube, not the center of the cube. Okay, that's a problem. You see, we are applying the geometric inversion to all the centers of the cube, and let's see what happens. Let's say 0.1. Okay, let's just give it some. Okay, so now you got this kind of thing. Okay, I have to think. I have to think about this. So our formula geometric inversion 3D takes a point and the circle origin, center of the circle here, ABC, then the radius, then the result is that. Okay, so for example at this point the result is that. Okay, so this is a geometric inversion of a point in 3D. Okay, so this function transforms a point and returns another point in Euclidean R3 space. And so now we got a bunch of cubes. Okay, let's. I know what to do. Discretize cubes. You see, we are applying the transformation to each cube, and a cube is specified by a center and the length of the cube, like that. So, but that's not what we want to do. You see, what we are actually doing is just moving the cube around. It doesn't change anything. We are just applying the geometric the inversion to the center of the cube. We just move the cubes around. But what we actually want is let me show you. Okay, discretize circle. Okay, so I can show you what we want to do. We want to consider the cube not just a atomic thing. We want to consider we want to consider each, a cube is formed by several lines, right? Several lines forming a cube. We want to, right now we are just consider a cube as one single point. That's not good. What we actually want is to consider the cube as let's say 1, 2, 3, 4, 5, 6, 7, 8, the 8 corners of the cube, and transform those corner points. Okay, then we will get a better result. But actually what we really want is to consider all the points in the line that makes up the cube, transform all that points. So in order to do that, we can do a I believe this is the function discretize graphics. Discretize a 2D or 3D graphics into a mesh region. Okay, so let's try that. Okay, I'm not sure this works. I'm doing this for the first time since like 20 years ago. So this is new function. Wolfram language has lots of new functions. Okay, so let's discretize graphics. Let's see what happens to when we do a cube. Okay. Okay, so what is the actual structure of that graphics full form? Okay. Let's see. Okay, so you got mesh region. Okay, so you got the mesh region. Yeah, okay. Okay, now you got tetrahedron. Okay, tetrahedron. So you got, what is this? Mesh region. List. You got two lists. Mesh region. List. So a bunch of lists, and then I'm not sure. Okay, that's not what we want. Not the mesh region. Okay, we want actually, I know what we want. So we want actually, you see, the mesh region, the discretized graphics basically breaks the graphics down to lots of bunch of points. So you see, a circle becomes lots of points. That is the essentially what we want. But in our case, geometric computation. So what are we doing? So this is annoying. Cube. Okay, polygon. Yeah, I think I know what I'm doing. We want canalized polygon, something like that. So polyhedron. So we want to turn a cube into okay, here. Canonicalized polygon gives a canonical representation of the polygon poly with shared coordinates. Okay, so let's try that. So what happens if you do that to cube? Yeah, that doesn't. What? Okay, so polygon. So I actually not polygon. We want polyhedron. Okay. You don't have. God, we stuck. This is taking longer than what is it supposed to. Shit. Yeah, okay, there it is. Yeah, there it is. So yeah, that's what we want. So let's see what is this. So we got a polyhedron. Let's see what is the structure. Why is it polyhedron? Why is it a bunch of lists? Okay, I can do this, but my explanation of how it works will not. I can just start to code it, and in 20 minutes it'll be done. But I don't think I can explain all the way to it. So we have to. So let's see. So we got cubes. We turn them into polyhedrons. And polyhedron is also new, around 2006, I believe. Oh, 2019. So it's very new. 2 years ago, 3 years ago. So, and what exactly is the structure of polyhedron? It fairly complex. Okay. So polyhedron boundary faces. Okay, polyhedron. Okay, this is more complex than I thought. Why don't I just go my way? Just do the way I would. So we begin with 2D, and now we ventured into 3D. Now, in either case, this is not a huge jump because it works similarly, either in 2D or 3D. So we can continue on with the 3D case, no problem. And for the 3D case, you'll see more spectacular graphics, which is good for doing YouTube. You'll see. I'm gonna show you spectacular graphics, which I actually never done before, even in the 1990s. Geometric inversion of three-dimensional objects. So that's what I'm trying to do now. So let's continue with 3D because it does not add much complexity at all. They work in the same way. So, but the problem right now I have is, okay, let me just talk over. So like talking to myself and it'll be better as well. So let me have a drink. So we're gonna push on with the 3D case. We want to do geometric inversion of a bunch of cubes or a grid, a rectangular grid in three-dimensional space. We want to invert it with respect to a sphere in the center of the coordinate. Okay, so we have our function here. So this function is defined that way. It's good. So it's correct definition. Geometric inversion of 3D given a point and a circle and radius, it returns a new point. That's good. So now, but we want to see the graphics. We want to see what happens to this bunch of cubes when you apply okay, so I think I know what to do. So okay, so hold on a second. So a cube, given a cube with its center, yeah, I know what to do. Okay, so given a cube, we are going to write, the result actually will be one single line, like no more than 200 characters. I mean, the whole code will be no more than 200 characters. I'm just stuck in the process, okay, but I can finish maybe in 20 minutes. So here is what we want to do, okay? So cube, so we have a cube and radius. So we want to transform it. We want to transform it into each cube. Let's see. Let's do it the silly way, okay? Let me do it the kind of the primitive way. So I mean, the focus is just to get it to work. Then we worry about the, elegance of the code or stuff. So cube. So P is the point. So we want to turn a cube into a polygon. Did we succeed? We want to turn a cube into a polygon. So discretize graphics. But what is the? I want to show the actual data. Mesh themes. No, I don't want mesh theme. Pretty. Okay. So you got the mesh. So what kind of but what is the structure of this thing? Decorate a mesh. What the fuck is this? View options. $3D print. So we got a mesh here, embedded dimension 3, geometric dimension 3. But I want to see the actual code. I mean, what the, like this, okay? So actually, so like that. Okay. So actually, I can see the code. Yeah, so here is a better mesh region, a bunch of, so mesh region, then tetrahedron. Oh, okay, so here mesh region, the way mesh region works is that the first argument is a bunch of coordinate points, okay, data points in 3D in this case. Each point is 3 coordinates. Then you have a tetrahedron, and each of its arguments, the number refers to the index. So for example, here you have a tetrahedron with points with the the corner point 7, 6, 1, 5. That means the 7th points in the data here, then the 6th, then the 1st, then 5. That forms a tetrahedron, okay? So how did we get this? So yeah, so we turn a cube discretized graphics. We turn a cube into a bunch of tetrahedron. We turn a cube into a bunch of tetrahedron, into like like 1 2 3 4. How many? 1 2 3 4. 1 2 3 4. 1 2 3 4 5 6 6 tetrahedrons. Wait, how is that? Okay, so 6 tetrahedrons. We turn a cube into 6 tetrahedrons, and why is there no option to show transparency? What the fuck? Okay, so we turn a cube into six tetrahedrons, and the structure of them is in this. That's the structure of the expression. Okay, once you have tetrahedron, then you okay, so let's do this. So okay, I know what to do. So cube, so change cube into okay, we are turning each cube into a discrete graphics. Okay, then we turn each tetrahedron. Then we turn each mesh region. Okay, then we turn each mesh region. Then we turn each mesh region. Okay, mesh region. So mesh region has got length 2, right? This is actually the code is not so great, but yeah, so mesh region got 2 arguments. Okay, so mesh region got 2 arguments. Then the first argument is a list of points. Okay, so data points. Okay, graphics. Okay, okay, so mesh region, we pattern match mesh region, match their arguments. Then we turn them into Okay, so I think so this needs to be a function. So you don't know what I'm doing, but I know what I'm doing, okay? Because you know the mathematical syntax, what is this ampersand and what is slash at, you don't know what I'm doing, but I know what I'm doing, okay? So data points, so we want to map them. Yeah, so we want to map that. Okay, so 00. And then this is no good. Let's just evaluate and see what happens. Oh god, this is gonna take a long time. This is incorrect, I'm pretty sure. What? What? Okay, I'm gonna finish this for sure. This turns out too much. Yeah, this is no good. Why is it showing this bunch of things? Idiotic. You know, thousands of them. Okay. That's not what we want. So yeah, this is not good. I have to think. Okay, so yeah. Okay, so let's reduce the number of, that's a lot of cubes. Let's say reduce number of cubes. Okay, there's still a lot. 5 times 5 times 5. Okay, so but let's say 3. Okay, 1 2 3. Okay, let's say, okay, so now it's much less number of cubes. Grid points. Wait, why is this cubes? Okay, so now it's much less. So now a cube, so a cube center, let's say, can we plus 1 1 2 3 1 2 3 4 5 6 7 8, so you got 8 points. Okay, let's look at the documentation for cube. Okay, so cube is centered at origin. Okay, so this output is no good, and we want to see what's going on with this. Okay, so that and that gives you a bunch of tetrahedrons. Tetrahedrons. So mesh region. So a cube returns a, you discretize graphics, a cube. What if you have some bunch of other numbers, 3 4 5, let's say radius 2. Okay, same thing, I suppose. Yeah, so this is same thing basically. Yeah, so discretized graphics of a cube returns a bunch of returns a mesh region, and a mesh region is, the structure of it is 2 arguments. The first part is data points, the second part is tetrahedron. So mesh region, we can transform mesh region, map. Yes, we can map. So this should work. We can turn a mesh region. So can we actually plot that? Let me try. Yeah, we can. Fantastic. Okay, so now we are back to our transformation process. which is here. So we are transforming a cube to any cube becomes discrete graphics. Okay, any cube becomes discrete graphics. Then for each mesh region, we map to then for each one we map it. Why is it not? Yeah, we got a bunch of okay, so what? So we do that, the mesh region becomes that. Okay, that, do it, man. Yeah. Okay, so we got that. Okay, so let's see. Let's say that. Okay, result X, then graphics 3D result X. Please. Yeah. What happens to our inversion? Didn't we just apply the inversion to the points? Our inversion did not apply. Wait. Did it? Not what? The coordinates given at position 1 in mesh region PDSG are not at least the real valued points in the same dimension. Okay, you got fucked up somewhere. What the... So mesh region, so it's just a list of mesh regions. That's correct. Okay, that's a structure of this expression it's a list of mesh region. Okay, now but why is it let's try it again. So mesh region, each one is 3 numbers. That's right. So mesh region, each one is 3 numbers. Okay, then cubes. Okay, let's do that. So what is the result? Okay, don't know what's going on. Z, so 0, so cube, you don't want to have a cube beginning at the region. So let's modify. So you got infinity 1 over 0 encountered. That is because when you apply geometric inversion 3D to something on the to a point on the origin, then you got that. That's right. So if xyz equals to 0, then okay, so we can modify the expression. Let's try to modify this expression. If let's try this, okay? Let's say 3, 4, 5 equals to 345.001 force, okay? But true, okay? So that works. So that's one way. So you can check. So if xyz equals to that, then just that, okay? Otherwise that. Actually, this is stupid. Okay, let's do it. So let's rewrite that. Let's rewrite that as let's redefine that as that. Now what? Oh, this is we got it wrong. This should be over here, and this should be over here. Yeah. We evaluate that. Do that. Yeah. Okay. We got. We need to redefine them. So clear. Okay, so now that's right. So now we got this definition back. Now let's save it. Save this. Okay, then let's try to do this. Now we don't have the we got rid of the infinite, division by zero problem, which may be a problem, because when you have that, then you do graphics, then you may run into problems. I don't know if that's our problem, but possibly. Okay, so now we got what we want. Let's see, cubes. Okay, so okay, now let's see what we now. What show stack trace? What now I want to understand what exactly is the structure of mesh regions. So mesh region is always two arguments. So why does it say the coordinate given at position 1 in mesh regions are not what the fuck? I don't understand. I don't understand. What? Okay, that is why. Yeah, but why are you giving that error? So we've been coding this for an hour and let's say 2:30 for 90 minutes already, and we haven't done nothing. We failed. Yeah, mesh region, you know. So mesh region is new. I know, I know a better way to, I mean, not, the classic way. you know, if I just do it my own way, I should be able to do it. But mesh region is definitely something I should use because it is, you know, now new part of Wolfram language. So what I can do normally is that, okay, save the so cubes, you know, so we got a bunch of cubes, then we plot it, okay, so we got a bunch of cubes, then we define our inversion, okay, that's a 2D case, then we define our 3D case by this formula, which is correct, okay, then, you know, and we test it, that's correct, then we let's see what happens. Yeah, kind of. Yeah, okay. Yeah, there's a translation. Okay, so basically this is about translation. Okay, so anyway, so this formula is correct. Definition of geometric inversion 3D. Then our problem is now actually generating the graphics. The formula is correct. So cube. Let's see how many face. 1, 2, 1, 2, 1, 2, 3, 4, 5, 6. So you need a 6 face of a cube. Okay, let's do it our own way, shall we? So anyway, I need to turn a cube to a bunch of polygon. Now I don't understand, you know, so how do I turn a cube into polygon? Back to the question. I mean, I can do it manually, but I want to be able to use Wolfram language. What? Canonicalized polyhedron. This should work. But what does it return exactly? It returns a bunch of rational. Yeah. Okay, so it returns a bunch of it's a polygon. Yeah, that stupid standard form. So it returns a, so cube becomes a polyhedron, okay? A cube becomes a polyhedron. Yeah, this is, okay, so I should use canonicalized polyhedron instead of discretized graphics, because this is a better, okay? So cube becomes a polyhedron, and polyhedron has 2 arguments, okay? So let me show you. So polyhedron has 2 arguments. The first part, yeah, you know, the first part is a bunch of points, okay? The second part is a bunch of polygons. They specify how, yeah, okay, so, yeah, so let's do that, okay? So let's, instead of discretized graphics, let's turn that to, yeah, so this is what we want, okay? So input form, that's right. So this is, you know, so it becomes a bunch of polygon, okay? A cube becomes a bunch of general polygon. And the polygon has 2 arguments. The first part is data points, a bunch of a list of points. The second part is the indexes that forms each face, a polygon, okay? so you know, each one of these group of numbers is a polygon that forms the face of the polyhedron. Okay, so now, so we turn a cube into a bunch of polyhedron. Okay, then we, okay, so then we, okay, so then we so a bunch of cubes becomes, okay, so copy that. Let's do that. Okay, so yeah. Okay, so that's what we want. Then anyway, so that's what we want. Then, so we got result x, then result x becomes, let's see, polyhedron. So polyhedron, the first part is a bunch of points. Then, okay, then we're gonna map our function to it. Okay, so map our function. Wait, is there a zero vector? No. Let's do it. Fantastic! I think that's it. Okay, now we got result 2. Save it. Let's see. Show it. No. Result x. No, nothing changed. What the fuck? What happened to our transformation? Why is it our transformation not applied? First argument, second argument. Did we make a kind of a silly did we make a silly syntactical error? Oh, now it becomes what? Now it becomes one single cube. What the? Okay, I think the problem is me have not been coded Mathematica for a long time. I might have made some very simple error. what is result 2? So result 2 is a bunch of polyhedron. Okay, so if we make this into a standard form, so polyhedron, oh, you see now, each one of them have a different shape. Yeah, so that's what we want. Exactly, so our transformation worked. You see, each one of these cubes become kind of funky. Exactly, because we applied our geometric inversion on the corner points. Okay, so it worked. You see, especially, look at this one, dimension type polyhedron. Did we spell something wrong? So result 2 worked. Okay, but when we show result 2 in graphics 3D, why is it not showing fucking nothing? Why is it just showing one single cube? Code Bamboo, you are still here. So can you talk more about your 20s and aspiration to be the best mathematician? I'm in my 20s and have similar aspiration about programming. Oh yeah, it's simple, it's trivial. Now, I became what I became is because that's a great sidetrack. Okay, so I got excuse to talk about something else. But actually, I should finish this because we are so very close. This is just me walking. I'm surprised you're still here. So okay, so yeah, so I wanted to be a great, I did, I was kind of a weird guy, very ambitious. I wanted to be one of the greatest mathematician, okay? Like like top 10 in history. That was I wanted to become. And I failed very badly. I'm not even a professional mathematician. Well, that is my personal life story, and there are some reasons for that. Well, you could say, put it simply, one reason is that because I procrastinate, I have a problem. Or you could say I didn't work. Anyway, for some 10 years I didn't work for various reasons, so I become very poor. I live in poverty, below poverty, and then anyway I just didn't become. So because I didn't work, and that's not good. You don't have money, and when you don't have money you don't have food, and when you don't have food you cannot do anything. So that is my personal problem. Okay, and my problem, my story. But if you are a programmer, it's unless you are very very extreme, you happen to be like me, but there's something wrong. Okay, you'll be fine. You do programming after 2 years, heavy study, code every day. Code 5 hours a day. Don't push yourself. 5 hours is good enough. Persistently, on average, statistically, if you code 5 hours a day for 2 years, you can essentially work for any big giant corporation you want. Now, coding is just very vast. Coding is, there are so many different fields. There's gaming, there's operating systems, there's networking, there's kernel, operating system, there's low level, then there's scientific coding, like we are, and there's educational. What I'm doing right now, coding this thing, is kind of educational thing or part of scientific coding, which you need to do if you are a mathematician or if you work for NASA, for example, or if you research AI, for example. These days, very popular, very common, and very highly required, needed skill. So, yeah, so I mean, today, there's a lot need for mathematicians now, especially with the AI age. So, yeah, statistician also. So anyway, so if you want to, study math or programming, especially programming after 2 years, you'll be good to go. And you'll have bread for life, just like me. So I was doing fairly well, but it's hard to say, when your life, why it happened. I just became kind of, maybe partly because I'm too ambitious. Okay, I despise lots of things. Google sent me, back in 2005, Google, sent me a request. Oh, we like you. Maybe you are like to work for Google, and I didn't. I kind of ignored it. So anyway, so yeah, so that's my problem. Okay, for many reasons, how to say. So anyway, so let's continue. I want to continue what's going on. Exploration of the Wolfram language, which I haven't coded for 20 years. So let's come back. Actually, I'm also getting tired. So what is our problem? So does that sounds good? I already have 10 plus years experience, start at 14. Okay, so what is your, like, what question? What do you have any specific question or specific aspect you want to ask me or something? Yeah, because I don't know, because there are so many different people in the world. I have, especially for me, my followers tends to be not the normal American. Okay, it tends to be all over the world, in Russia, in Middle East, in Africa, in South America, all over the place, in England and Europe, in Germany, and in Japan, in Hong Kong, and also in China. So I don't know what's your background. I haven't, I don't know you. I don't know if you are on my Discord, and especially with you guys, anonymous name. So anyway, I don't know what kind of person or what kind of, this is very diverse. Like, I cannot imagine, like, you see me, you kind of know me because you see my face. That tells you already lots of things. But online, you don't know who they are, so I don't know what's your specific questions or what you want to ask me about. Okay, so but yeah, so I hope you do good. I love programming and I love math, and especially I still have the opinion they are the greatest thing. Of course, for many people, they cannot do it. It's not suitable for them. Oh, I'm not good at math. Oh, well, even I don't know anything about computers. A lot of people are like that. So for them, maybe they go to leadership, they go become politicians, or they become businessmen. Yeah, okay, fine. But if for many of my followers, we are into, we are nerds, we are into programming, we are into computers very much. So it's a very great job and profession, and you don't actually need to go to university. So I'm basically self-taught. So yeah, you can do that. I'm bored of the web dev. Yeah, what is worth going to programming wise? I want to make what you call permanent work. Okay, so now that's a different question, because now you are picky. You are tired of web dev. And you want to, yeah, so I don't know, that you have to, I mean, you have to find out yourself. There are so many, I don't know, sysadmin or whatever, game dev, I don't think there's, I don't think it's gonna be ideal, you know, because when you go into another field, you'll find, oh, it becomes boring. Also, it depends on the company. So I want to get some coffee actually. So I'm kind of anyway, I'm tired. Let me get back to this. So what's the other? Celtic Orthodox. Okay. Math Social YouTube. Lots of good books. Okay. Okay, so we kind of failed to do this, and I'm getting tired, but we are close because the result will be spectacular. Okay, the result. I'm not going to show you some Wikipedia, but anyway, I'm very close. Okay, but I want to finish this. So we are so very close. So why is it? So yeah, so we got the result. So result 2. Result 2 is showing one single cube. That's definitely fucked up. What? What is this? So we have so many polyhedron. But why is it when you show in graphics, it just one of them? I mean, this is okay. That's it for today, I guess. I'm tired. I'm gonna. So I talked for 90 minutes and kind of failed. That's a pity because I'm so certain that I can do this. Shut down or not? Yeah, and it's shut down. I work this offline. Maybe I'm gonna delete this live stream. I work this offline so I get a better sense. Then maybe I'll do another one tomorrow or sometimes later, so I can show you. I can instead of you watching me, fumbling around, I'll just show in 10 minutes explain everything and show the spectacular results of inversion. Okay, so that's what we are talking about. Inversion. We were going to code this, and I thought of why not, let's just do 3D case because it shouldn't be more difficult. But it turns out we didn't finish. Okay. Thank you guys for watching. Bye guys. Okay, so I'm gonna shut down in 2 minutes. There's something truly weird here. Hey Bart, you still here? See you next time, Bart. Thanks for coming by. Okay, I cannot believe this not okay. So now it shows. Okay, hold on a second, guys. I think I got it. There it is. Okay, let me show. Hold on a second, guys. Don't go yet. We did it. Fuck. What? Hold on a second, okay? We almost did it. We almost had it. So what the fuck with the graphics 3D? So something. Yeah, so you know, if I show just part of it, you see, so you can see we got, you know, we got a bunch of cube inverted, geometric inversion. But however, right now the problem is that for some reason the graphics is not showing them all. It's, you know, it's just showing one of them. I don't understand. You know, probably something trivial because I'm getting tired here. You know, so if we see the result too, you know, the structure is that it's just a bunch of polygons. Okay, so they are, you know, they are, you know, let's say dimension. Okay, so 444, you know, it's a nested matrix. It's a list of 4 items. Each one is another 4 items. Each one is another 4 items. Okay, so why is the list of a polygon not? Okay, so let's try this. Okay, I know what to do. Okay, hold on a second. So why does this works then? I don't understand. So we got a total of 64 of them. But why is that if you put in a graphics it does not show? Okay, I don't know, I give up. Hey, Ztron Crazy, what's up? Okay, okay, why don't I figure this out? Because this is very strange. So now the problem, you see, now the result actually contains the correct graphics, okay? So here's our result true, that's actually correct, contains the correct graphics. It is a nested list of 4 items, then another, each one contains 4 items and 4 items, okay? So dimension is 444, a nested list. But the problem is that if you show it in graphics, it doesn't show the fucking thing. It just show one cube. But however, if you show, you know, part of the, you know, the list, you know, if you extract the result, then it shows, you see. So I do not understand what's going on with these primitives, okay? So I do not understand what is going on with this. Okay, let's quit kernel and let's start over. Maybe that will fix things, because this is pretty odd. Okay, let's start from the beginning. First of all, save the buffer, compute 3 plus 3, okay, delete that, okay, then points we don't need anymore. Then we start to compute, so cubes, okay, so we do cubes, okay, then we show cubes, okay, that's good. Then we define our function, geometric inversion 3D, okay, then we test it correct, then we transform our cubes Okay, wait, this is not what we want. We transform our cubes expression, which is this, you know, this bunch of cubes. We transform them by replace each cube by canonicalized polyhedron. Okay, we do that. Okay, then here's a result. Essentially, what is this? Essentially a list of input form. Okay, so essentially it's a list of polyhedrons. Okay, so result X is a list of polyhedrons. Now let's try to show result X to see if that works. Okay, so yeah, that works. Okay, because we haven't converted, we haven't applied the geometric transformation yet. So, you know, let's show it. For example, wait, what? Nah. All right, so, but now result 2 equals to result X. We transform it into a we do that. Okay, so we got at least a bunch of polyhedron again. That's result 2. Then show the input form. That's good. Okay, this is too long. Then show the dimension. That's good. Result 2, show it. Got same problem. But now if we show part of it, oh, I know what's going on. I know what is going on, you know? The reason you are seeing this whole thing in one cube is because all the rest is inside it. Because remember the inversion. Yeah, the inversion inverted, inside becomes outside, outside becomes inside. So on the outside you have the one giant cube. Is that right? Yes, they all be, I think so. I'm pretty sure. Okay, so now let's do some transparency. Opacity 0.5. Okay, let's do it. Okay, so wait. Okay, so these two needs to be in the same together. Okay. There you have it. Fantastic, my friends. Ah, finally. Okay, so this is spectacular. Okay, so you are seeing just part of it. Okay, you see. But now let's make the whole thing. Okay, now let's clean up the whole thing and let's make it truly spectacular. Okay, so this video, I can say after 2 hours I fucking did it. Okay, so cubes we don't need, so let's make this clean. Okay, cube, yeah, we need cubes. Okay, so but instead of from 0 to 3, let's say -3 to -3 to -3 to 3 to 3. Okay, So now we got massive number of cubes, okay? So now you show it. What? Oh, okay, 0, 2, 3. We forgot the negative sign. Yeah, so now we got massive number of cubes. Do it, then show it. Fantastic. Okay, now wait a minute. Now I want some transparency. Okay, so opacity 0.5, then cubes. Okay, do it. Okay, so now we got a massive number of semi-transparent cubes. Okay, now save it. Now the 2D case we don't need. Let's clean up our code. So the 2D case, delete, delete, delete. So now we define our three-dimensional case, geometric inversion. Okay, and the test works. Okay, now we actually, let me truncate this. Let me just show you the one single result. Instead of me fumbling before, let me show you the proper way, because I made a mistake. It's a silly mistake. So let's review what is a mistake. Because I forgot that geometric inversion, it covers your cubes. That's why you don't see it. Of course, I don't see it because the outer cube covers the whole thing. So I doed about nothing for about 40 minutes. Fucking idiotic. Okay, I wondered, why does this not work? I know it should work, but it's not working. So I doed about nothing for 40 minutes about. So anyway, so our function works, geometric inversion 3D, then the expression here will be this. Okay, so now I know what I'm doing. This should be that. Okay, we don't even need the result 2. Okay, so delete that. So let's see. So do it. Okay, now you're gonna have massive you're gonna have massive number of polyhedrons. Okay, okay, I want to hide the output. Just don't show the output. Output takes a long time. Okay, so that, okay, so that, okay, so now opacity result 2, wait, not result 2, now result X. Okay, we fucked up somewhere along we fucked up again. What? Geometric inversion 3D, do it, and result X, wait, cube, oh yeah, becomes what? We fucked up along the way. Yeah, okay, so it's better split this. Okay, then. Okay, so result X is that. Okay, then result 2. What the? I clicked mistake. I clicked some feedback thing. So now result 2 equals to apply the polygon. Then let's do it. Oh, I forgot. Actually, this should be that. Yeah. So now, what the fuck? Oh yeah, X result 2. Wait. Okay, now we have better graphics. Okay, so now I'm going to show you. We need to remove the outer box. Okay, so now you kind of see we need to remove the outer box. Let's do that. Okay, remove the one in the middle, because when we begin, you see we have this bunch of cubes. We have one in the origin, and that one after inversion becomes that giant cube. So let's delete cases. Okay, so cubes, delete cases. Okay, wait, cubes equals to cubes, remove one of them. Okay, do it. Okay, so here's the result. Then do it. Do we still see the one in the middle? Yes, you see it's gone. You see it should be there, but it's not there anymore. So okay, so now we do it. Fantastic. Okay, now we want viewpoint. Okay, plot range. Wait, so it becomes 0, 0, 0, 1. Okay. Let's say 9. Okay, that's it. That's a result of today's thing. I'm getting tired, and this is, okay, not bad. Okay, let's say not bad. So this is a result of a geometric inversion of a bunch of cubes in the plane. I mean, in 3D, in the Euclidean space R3. This is that's so you can see how it is similar in the two-dimensional case. Okay, so finally that's it today. So I'm gonna let this image sit for a while so that YouTube will pick it up. Yeah, that's it. I'm gonna shut down for real this time. Shut down for real in a minute. Let's go into it, dive in. Let's see what happens. So we are diving in. We are diving into the inside of it. It should be more spectacular. Yeah, so let's say not opaque. Let's see what is the effect. You trial and error. Okay, so actually we can, there's something more fun we can do. Okay, so let's, so now we are just showing, now we just have this many. Okay, in fact this formula will go to the top. Okay, and now okay, we are cleaning up the notebook now. Yay, fantastic. Okay, so let's try that. Bye.